So before we start, I've been in the telecoms industry for like 13 years. And I so enjoyed the two previous speakers before me, because what I started with was doing test automation. And I made my own test automation framework. So all of that is highly applicable, I can tell you, especially if you decide to do it in TCL, which is a wonderful language to work in. And especially if you also find a way to make TCL what's called object-oriented, and you put that on top, then you are in for some 10 years of fun. And also I spent at least 100 hours debugging regex. So there's a lot of good things from the conference so far. But I am here to talk about time. So I've been invited here by our partner iTectra to basically talk a little bit about time. So time is quite interesting, to be honest, because it's a very simple concept, right? Time goes forward like one tick at a time, but yet it's so damn complicated at the same time. So why do we need time? Why do we need to deliver time with our networks? Yeah, I guess some of you have had the joy to try to troubleshoot logs from NEs that has not been timed with the same timing. So it's more or less very hard to understand if events were concurrent or not. That is like a audit-based application. And I mean, we have the financial stuff there, who was really first of making this trade, who should have precedence over the other. And I mean, a lot of people really like to collect a lot of data, often streaming telemetrics. So time is becoming more important, right? But what really makes me and my company throw a lot of dollars investing in being good at time is the mobile industry, because that is just so much money with 5G, and they need time to do beamforming of antennas, so they basically can do spatial division multiplexing much more efficient, so they can reuse their spectrum more often and give you guys more to do next year managing the backhaul of all those data. But also, I mean, media distribution, we have power and utility, I think everyone is aware of. And also there are quite a lot of governmental stuff that is also quite interested about time, where you can do also phased array things with radar station and stuff like that. So there is a need of time. But then what is time in a network? So I guess all of you, or at least some of you, has heard about something about synchronous Ethernet. So basically sync E. But sync E is a frequency. Like if every one of us were clapping in this room, I mean, we wouldn't clap together at once, right? This will be like everyone starts randomly, and it will be this thunderous applaud. That is what you get with sync E. But it might be that we actually want to clap together, right? To build this kind of rocket clap like the Icelandic football supporters did quite a few years ago. Then we need something else. Then we need also phase, because we need to do this in unison, right? And if you have frequency and phase, yeah, then we have time, right? Because phase is, yeah, basically we say now is time 0, and after that we can decide what any other time of these waves are. But this cannot be so damn hard, right? I mean, we have MTP. I mean, if you ask me what my clock is, I can say, yeah, well, it's obviously wrong. But I can tell you what the clock is. right? And how hard is it? So if us in this room were super good at clapping together, I bet if it's inaudibly bad, we do this. Yeah, we have like 3 milliseconds about-ish before it starts to smear out to our audio senses. Okay. Then we do that 1,000 times tighter. Then we are on microseconds, right? And microseconds, that's pretty neat, right? But the technologies that I am talking about here takes us 1,000 steps down again, down to the nanosecond. And then we get a little bit of inaccuracy, me here reading my clock to you, because yeah, information takes a little bit of travel, right? So we need to figure out the latency between us. And how is that? Yeah, well, I can say that my clock is 12. You can look at your clock and see it's 5 seconds past 12. Okay, it was a 5-second propagation. But wait a minute. You don't have a clock, right? Because the mission of the protocol was to transmit the clock. So unfortunately, the only thing we can do is to measure the round trip delay. And in a network, I mean, that can be messy, right? Buffers filling, not filling, you have jitter here and there, stuff is happening in a real network. But we can throw statistics of that on that shit, right? Just measure a long time, get a nice graph over a long time, and we see some medium, and we can take that. Yeah, well, maybe our regulation becomes a bit slow and stuff like that, but that can be okay. But there is another core assumption here that is really nasty. That is, for this to work, we must assume that the latency from me to you is the same as from you to me. A to Z equals Z to A. Because we can the only safe assumption we can do is that me talking to you is half a round trip. And if this is not true, we cannot see, 1588 cannot see this error, and it's called an asymmetry. And that you can calibrate away, right? You can just manually add a little bit. But if some operational conditions change, you may need to go and recalibrate it. And what is the only way to find a calibration for this? It's 2 very expensive clocks on both ends of this that you need to run for a while and see the unidirectional latency. So yeah, I guess I've already been answering a little bit these questions, right? So it is not really solved unless you're careful. And I will give you some good examples of that as well. So I know you guys are probably happy with seeing routers connected to each other, but typically there is a transport layer underneath that can make your timing life really crappy. No, back. Hello? Yeah. So basically we have contributions from the equipment that can be asymmetric in itself, and also the effects that we are using in the transport in order to go really fast, really long. Okay, this has some kind of auto move. And also we can have things in the line system, like the fiber lengths, they may not be the same, right? And just as a reference here, those 5 nanoseconds, maybe we would like to have. Yeah, that is equivalent to 1 meters of fiber, the distance for the light to go in 1 meters of fiber. So it's, you need to do this length matching really well if you're going to have it bi-directional. And also you have OTN mappers, and they have FIFOs. And I mean, there is in a classical OTN mapper, there is no communication between the ends on the buffer level fields and stuff like that. But when the line comes up, it comes up, right? So there you can get a buffer fill asymmetry that will never go away. So some of these are so-called fixed time errors, like the fiber. I mean, it doesn't change. It well, it can expand a little bit with temperature, but let's pretend that that is not the case. And then you also have this random CT time error components that basically is either different at each boot up or varies with time. So a lot of the technology that are in this domain is basically targeted to solve this transport problem. So a mobile network, depending on between which units we are talking about, yeah, typically we have a time error budget of between 60 to 1,000 nanoseconds. If we are doing backhaul, or if we are actually in the part where the antennas need to do this very quick and synchronous processing. So I want to show you this picture because a lot of the technologies, as I say, is driven by this problem. In the 1588 protocol, there are two clock types where most people only get exposed to one of them. So you have the boundary clock, which is the normal one. It's the hop to hop, and you have signaling between each router hop or switch hop that you have. And there you process the full stacks as well. And there you have these performance classes as well. So yeah, that is also a wonderful pitfall, right? If you buy a class A boundary clock, yeah, the max time error here says 1,000 nanoseconds or 100 nanoseconds. But if you have an asymmetric transport system underneath, I mean, that is not at all the max time error. And then we have the transparent clock to the right, where we do not do the full stack processing, but we have in the ingress pipe, we just see, oh, this is a 1588 package. We timestamp it when it comes in and put that in a meta header that gets processed with the packet in the pipeline. And then the switch does its things, right? Or the router does its routing and see, okay, where is this going to go? And add a little bit of random latency here and there, right? But then at the very egress, we hardware timestamp again, and we deduct the difference and put that inside the frame, like a justification. So basically, the transparent clock can magically remove the jitter created by the packet processing in the switch or the router. So you see here for 1588 clock types, the boundary clocks have performance classes, but yeah, the transparent clock cannot really have a class of performance since it doesn't do the full stack processing and stuff like that. So it's basically what we state there is the resolution on how well we do the timestamping. So on the XH800 unit, for example, we have 1 nanoseconds max error coming in and 1 going out. So then we add maximum of 2 nanosecond error per frame. But also remember that this is very high frequency jitter, right? This error. So if you have a decent boundary clock, it will filter this away. It will low pass filter a lot of that noise away. So basically, yeah, good transparent clock will not add any, more or less any noise on the end to end. So, but a lot of people is not that exposed to transparent clocks, and it's not that broadly implemented in the industry either, and a lot of people just doesn't really see this as a viable solution to a lot of problems. Also, another wonderful thing about the transparent clock is that through the NE we can run an infinite number of timing domains, because we do not really interpret the timing with us, and we do not we do not terminate the protocol basically with the transparent clock. But the boundary clock, there we can only have one clock domain, because we are adjusting a physical clock inside our NE based on this information and the output of the 1588 servo. So let's see some ways on how we can address things. So first of all, don't put in shit stuff in networks. So we are quite open with that certain ASICs that we have are not at all suitable for transport of 1588. And it's not that OTN is necessarily bad, right? Because we have some OTN cards that are super good as well. But your supplier should know this when they are offering stuff to you for a timing application. So talk with people who are transparent with that, and help them to help you, so to say, put a good solution together. So let's stop a minute for a war story. So this is something I did last year. I have a large customer here in the Nordics that was testing the routers through our older OTN cards, just a transponder. And they saying, yeah, why do I get line glitches on my transport gear when I start off 1588 on my routers? And we like, well, you shouldn't, kind of, right? But then we looked more on this, and we connected our testing gear to it as well. So basically what these routers did was that they were also deriving sync E from this PTP, and it was too fast to regulate, so it got much way out of the sync E standard. And an OTN card, it has a certain amount of clock stretch you can do before you have a buffer overrun or underfill. And if that buffer goes away, then you get a line glitch. So basically, people can have 1588 inside their products and do them wrongly. It's not one size fits all here. Also, what one can do is something that we called OTC, optical timing channel. I was talking about that, 5 nanoseconds, 1 meters of fiber. Yes, length match that. I mean, it's first break, some guys come in and screw that up, right? So what we would like to do is to put bidirectional optics and run it through one of the fibers only, right? And also, one can have boundary clock on each hop if we want, but here's an example that we did together with a customer on some 7 hops, 1588, and we have a total timer here of 12 nanoseconds, which is quite good because each of these are class D, so they are allowed to have 5 nanoseconds error each. But yeah, if you get a load of these thrust, it's not very likely that they will all be wrong in the same way at the same time, right? Yeah, this one we will skip. And this one will also skip. It's not that fun. This is fun. So performance. Reality is not lab here. So this is from a unit that we developed 2 years ago. And we say that this is class C. So there you're allowed to be 10 nanoseconds off. But I mean, if you look at these measurements here, the ideal TC output, it's 2, right? So, and 2 is much smaller than 5. So why am I saying class C and not class D? Right? It sounds like I'm doing a very bad job on selling my stuff. Or that we have something called reality as well, where like you have changes in temperatures, humidity, and that is when these kinds of stuff becomes much more tricky than just standing on a lab bench in our nice cozy 25 degree. Here you can see also the constant time error impact from the transparent clock. It's like 1 nanosecond, which is quite good. Exactly, and it obviously the stuff that we sell to you, they doesn't only need to work well today. They need to work in like 15 years as well, after some kind of quite heavy physical abuse. So we are promoting 3 different ways of dealing with synchronization. The first one is wonderful because we can just okay, back. It doesn't want to go back. Hello? No, it doesn't want to go back. Yeah. Okay, fun. So the first one strategy is to pretend that this problem doesn't exist and just continue as normal. And if you pick out the right stuff and if you have the right sort of requirements, this is actually a viable strategy if you have the right vendors in your network, etc. Or you can put in this optical timing channel in, and that you can do with either dedicated boundary clocks or reuse boundary clocks from the network equipment. And also you can do this in hybrid, of course, which is basically what we have done here for our customer in forward one, please. I think this one is a little bit dead. What? Okay. Forward one then, whoever has the laptop. Fantastic. Let's see if I remember what was on the next slide. Yeah, so we had, this is an actual operator in the UK that built a timing cloud. So basically to their PE layer, they have timing SLA. So there they want to have clean, sure demarcation of not having more than 100 nanoseconds off. And then depending on the edge application, yeah, they can go sloppy or they can continue this nice, excellent cloud. And this is a pretty nice solution that we put together to them based on the OTC. Tack så mycket. And I think it's important also for you guys to understand that time is a network service. time is not just a function, it's a service. It's as important as many other aspects. And it needs to be treated as such when you are getting customers with these requirements. Okay. I think we totally lost some... Okay, takeaways. Synchronization is not trivial. Talk to a friend. And we have a lot of friends and partners in the industry. So borrow from the expertise that you have around you in this area, because a lot of stuff is not super intuitive and there is no clear heuristics. I shouldn't use that technology or that technology. So my recommendation is really to talk with the experts, and also you guys can hook up with me later at the social, and I can talk how important it is to make mistakes, like and make them early, like disconnecting Ireland, for example. That was very popular. Okay, thank you very much, and see you later.